So whenever we do these, they'll be recorded, which is why you don't have to have your mic or your camera on unless you really want to. Once it's done, and it sends me the compile thing, because I'm doing this through my own Zoom account, it'll be posted here, but there'll be a link in Canvas to it. This is my YouTube channel. There are a ton of videos. Some of them probably covering a lot of the same homework problems or lecture material. This is all from basically when we were in COVID and we had to do lecture online or homework sessions or whatever we were doing. So if you ever do want to come check here, some of it's my Irvine Valley and we use a different book. But there are videos here. Why are you crying? And that's my dog. She might be a little annoying. Hopefully she won't be too annoying. Yeah, chill out. Go play. But anyway, so once this is done, it takes like an hour to compile over in YouTube and then I'll post a link. So I don't know, sometime this afternoon it'll be up. Anyway, if you go into my lab mastering, hopefully you all have your accounts. I know that some of you do not, and I hope you do. Get them soon. We're going to cover chapter 1 and chapter 3. How this will work is I'm going to go through them. Your numbers may be different. So as we do these, just know that your numbers may be different, but I'll solve them using my numbers. If you guys who are here have a question, turn on your mic or throw it in the chat and let me know. And hopefully this won't take super long. I don't think it will, maybe an hour. What that is. No. So anyway, the first question, all of homework 1 is basically unit conversion stuff. Homework 2 is vectors, and that's really what I want to talk about, but we'll do these really fast. One thing to remember in SI, our units are always, SI units always have to be in kilograms, meters, and seconds. So this first problem, it should convert 77 inches to SI units. And if you want, there is a conversion in the book, but I never remember inches to meters. 1 inch is 0.0254 meters. So 0.254 meters is 1 inch and 0.25. So the inches cancel and we get our meters. So 77 times 0.0254 is 1.9558. But you can see that we only have 2 sig figs here in 77, so we should only have 2 sig figs in our answer, and that means about, I'm sorry, that should be in meters. So this is about 2.0 meters, should be our answer. Secondly, years to seconds, 3.45 times 10 to the 6th years. And I want to turn that into seconds. How I do this is there are 365, maybe there could be 365.25 days in 1 year. So my years will cancel. And then there are 24 hours in 1 day. And then there are 60 minutes in 1 hour. And there are 60 seconds in 1 minute. You see that all the units cancel off and we're left with seconds. So 3.45 times 10 raised to the 6th times 365 times 24 times 60 times 60 gives me 1.08 times 10 raised to the 14th seconds. Sorry, 1.087. So this should become 1.09 so that we have 3 sig figs, just like in our answer, or just like in the original value that they gave us, 1.09 times 10 to the 14th. And then finally, 69 feet a day. 69 feet per day. The idea here is that we need to be in meters per second, meters and seconds. So that conversion between feet to meters is really 12 inches, but 0.3048 meters in 1 foot. So that'll deal with the feet. 48 meters in 1 foot. But we still need to deal with these seconds. And so in 1 day, notice that the day goes to the top. There are 24 hours. And in 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. And we're going to end up with our units being feet go away, meters, days go away, hours go away, minutes go away. And we're left with 69 times 0.3408 over 24 times 60 times 60, and our units will be meters per second. So 69 times 0.3408 divided by 24 times 60 times 60. This is 2.72 times 10 to the minus 4 meters per second. Again, only 2 sig figs, so we're only going to keep 2 sig figs. 2.72 will be our, and I'm sorry, that's a little weird. I don't know why they are slightly off. They got 2.4. So maybe my calculation is slightly off. It looks like they used feet in a mile and then meters in a mile. So they turned feet into miles and they ended up with 2.4. So maybe my version here was slightly off. 3048. Oh, yeah, I'm sorry, you guys. Yeah, a little dyslexic. 3048. That's where my number went slightly wrong. 0.3048 divided by 24 times 60 times 60 is 2.43. So 2.4. I'm sorry about that. We only keep 2 sig figs because the original question only had 2 sig figs. And the big thing here is to remember that just make sure when you convert, if it's in the bottom, you convert the correct way, the denominator to the correct thing. And this last one, yeah, this will be recorded, Chris, too. So if you do miss something, you'll be able to watch the video and freeze it wherever you want. Let me know when you're ready. We'll move on. Oh, I'm so sorry. I'm like, you ready? Let me know when you're done, Chris. Thanks. Okay, so this final one, the reason why it's on here is we have miles squared and we need to turn those into meters. So we have 4.2 times 10 to the 4th miles squared, square miles. Whenever you have a squared unit, like centimeters squared or centimeters cubed or kilograms or something, you have to do the conversion twice or 3 times or whatever, because this is miles times miles. So the conversion between miles, 1 mile is 1609 meters. I know that one off the top of my head. So we're going to multiply this by 1 mile over 1609 meters, but we're going to do that twice. We have to do it for each of the miles in our units. And so what this ends up being is 4.2 times 10 raised to the 4th times 1609 times 1609. And I get 1.087 times 10 to the 11th meters. There are 2 sig figs here. So this is 1.1, and that's meters squared, times 10 to the 11th meters squared. Just make sure you remember that whenever you have a squared, you need to do it twice. When you have a cube, you got to do it 3 times. It's one of the places that students tend to get their unit conversions wrong, 1.1 times 10 to the 11th. Okay, so just a little bit on that. Our next one is, we're going to find the density. And density, I'll just move to here. Density is usually rho. It looks like a P with a curly tail. It's mass over volume. So in this mass per unit volume, we have a mass of 0.0189 kilograms. The units here will be kilograms per meters cubed for SI in physics. And we have 212 centimeters cubed is our volume. But we want kilograms per meter cubed. We need to change this volume into meters. So 212 centimeters cubed. Now there are 100 centimeters in 1 meter, and we need to do that 3 times. So we're going to multiply this by 1 over 100, 1 over 100, 3 times to get the conversion. Once we do that, once we have our volume, we're just going to divide mass over volume. So 212 divided by 100 times 100 times 100, or 212 times 10 to the minus 6 is 2.12 times 10 to the minus 4 meters cubed. Do not change your units yet. Don't use sig figs yet. But we get that our density is 0.0189 kilograms over 2.212 times 10 to the minus 4 meters cubed. And our answer is 0.0189 divided by 0.000212, or 89.15 kilogram meters cubed, or 89.2. 89.2. Why? Because there are 3 sig figs here, 3 significant digits after the decimal, even though there's 4 places, it's only 3 and 3 here. So our answer should have 3 sig figs, 89.2 kilogram per meter cubed. All right. And then we want, again, same thing. We want the density of a liquid with 95 centimeters cubed and a mass of 81 grams. So this one, again, we want our mass over our volume, but our mass is 89 or 81 grams, not kilograms. And our volume is 95 centimeters cubed. We can do this a little bit easier. 81 grams, there are 1,000 grams in 1 kilogram, and 95 centimeters cubed. There are 1 over 100 cubed meters, centimeters. And so this, before we deal with the 81 and 95, This is 1,000, 1 over 1,000 divided by 1 over a million. So this would be the same as 1 times 10 to the 6 over 1 times 10 to the 3rd. These would cancel. And basically, we're going to multiply 81 over 95 times 1,000, 4 times 10 to the 3. So 81 divided by 95 is 0.8526 times 10 to the 3rd. This is our density in kilograms per meter cubed. And we want 2 sig figs. So this would be 852.6 kilogram per meter cubed. But if you want only 2 sig figs, that's 8.5 times 10 to the second, 850 kilogram per meter cubed. Sig figs are a pain. You can just enter, I guess, 850 is what Master in Physics will allow you to do if you want, but that's the way you do that, is convert the grams to kilograms, convert the centimeters cubed to meters cubed, and then make sure your sig figs are okay. Although, like I said, I guess Master in Physics doesn't care about sig figs in this one. All right. And really, like I said, these are just unit conversions. 8 grams of sodium chloride and 1 milliliter is 1 centimeter cubed. Okay. And we want the we want our units. I was trying to read this because I was like, they didn't give me a volume. They did give me a volume. The volume that they said, if you read this carefully, is that there are 8 grams of sodium chloride per liter. So we have 8 grams in 1 liter of water of this sodium chloride, NaCl. And we want to convert that to kilograms per meter cubed. First of all, the 8 grams gets converted to kilograms by 1 kilogram over 1,000. That's easy enough. That's just 8 times 10 to the minus 3, dividing by 1,000. However, the 1 liter, so 1 over 1 liter, we need to convert that to milliliters first. And there are in 1 liter 1,000 milliliters. Remember, milli is 10 to the 3rd. So there's 0.001 liter is 1 milliliter, or there's 1,000 milliliters in a liter. However, for liquids, we assume that 1 milliliter is equal to 1 centimeter cubed in volume. So 1 milliliter is equal to 1 centimeter cubed. And then we need to multiply this by 100 centimeters per meter. We need to do that 3 times. So what we see here is we get 100 times 100 times 100, or 10 to the 6, divided by 10 to the 3rd. And so we end up with 10 to the 3rd. That is the conversion from liters to centimeters, or to meters cubed. Sorry. So we have 1 liter times 10 to the 3rd, which converts which is the conversion from liters to meters cubed. These these cancel, and you're left with 1 liter per meter cubed. So I want to go 1 over 1 liter. So anyway, this is our conversion. So what we get is we get 8 divided by 1,000 times 1,000, or we get 8 kilogram per meter cubed. Let's do that one more time really fast, just to make sure I'm right. 8 grams per liter. Now the grams go from 1 kilogram over 1,000 grams. So our grams cancel. And in 1 liter, there are 1,000 milliliters. In 1 milliliter, there is 1 centimeter cubed. And in 1 centimeter, there are 1 meter, but I cubed that, so 10 to the 6, 10 to the 6, and what I get is I get 8 kilograms per meter cubed. Okay, which is our answer, 8.0. Seems weird, but you've shown that the conversion between grams per liter directly converts to kilograms per meter cubed. Already. Now these ones are a little bit different. You can look at this, but this is about understanding what a graph tells you. And it's very simple. But when we look at this, this is height over time. And so you have to imagine this is a one-dimensional object. And it drops a little bit between, I'm assuming 0 and 1 second, drops a little bit further. The height change is increasing as it falls down. It's getting further and further and further apart. So even though this is a two-dimensional graph, this motion is one-dimensional. The object is falling from a height of maybe 247 meters, and it's getting faster as it falls. So now, the rate of change between these, okay, the change between them over time is actually constant. If you subtract any 2 points, that change is the acceleration. So essentially this thing is constantly speeding up by the same amount. You could say, okay, well, its speed is doubling every time. Okay, so each gap is getting, is increasing by a constant amount every time. If this was exponential, you might see an even greater change, but the object is shown to be moving at constant speed. Why is that not true? If these gaps, the change of height was the same between every second, that would be a constant speed. If the distance between them was getting smaller every time, that would be slowing down, right? It would be slowing down as it fell. So this graph is just speeding up. All right, again, we want to describe what is happening here. Starts at 0, begins to get faster and faster and faster until about 400 meters. And then it begins to get slower and slower and slower. The distance between the dots is the displacement. And so the displacement gets larger between the dots, and each dot is a second. So it travels a further distance between dots and then a maximum further distance. And then it starts to slow down because it's traveling a shorter distance between every dot, okay? So if we make a motion versus time graph, it's going to look something like this, okay? And that's all. I just want to make sure you guys can make a motion versus time graph. Hopefully it's not too much rotating. Map the motion versus the time. Whenever you have a graph, it's always given as y versus x, your y-axis versus your x. So if this was pressure versus volume, pressure is on the y, volume is on the x. I hope you've learned that already in lab, but it's always the same. Okay, so in this one, a jet is cruising at 300 meters per second when suddenly the pilot turns the engines up full throttle. After traveling for another 4 kilometers, the jet is moving with a speed of 400 meters per second. What is the jet's acceleration? So acceleration is the change in velocity over the change of time, okay? But it's also the change of distance, over the change of time, which is the velocity, over the change of time again. So when we look at this, he was traveling 300 meters per second. And then after 4 kilometers, so we started here, and after he traveled 4 kilometers, he was then going 400 meters per second, 300 meters per second. So his velocity change was 100 meters per second. If we assume this is constant, we could probably find the time, but we don't necessarily need to do that. What we want is to look at these diagrams. Constant acceleration means that these little arrows, which are the velocity arrows, they're the position over time arrows, these should be getting bigger and bigger and bigger. So these velocities are vectors that represent, or these green arrows are vectors that represent your velocity. This is constant. This acceleration would be 0. Again, this one constant. And if we look at the variables, we know he traveled 4 kilometers. This one's out. This one's out. So it's really down to this guy and this guy. The initial velocity was 300. The final velocity was 400. The initial time is 0. 0 and 4, 300 and 400, 0. But the difference between A and D is that these arrows, which represent the velocity vector, are all the same magnitude. And if the velocity isn't changing in magnitude or direction, the acceleration is 0. You're not speeding up at all. So this is wrong. These arrows are getting bigger because the acceleration is the change. And in fact, they're getting bigger by that same amount of that orange arrow. If you add that orange arrow, you get the green one. Add the orange arrow, you get the green one. Add the orange arrow, you get the green one. Add the orange arrow to the previous one, etc., etc., etc. So anyway, it's just making sure you understand visual representations. Finally, position versus time is shown, and select the correct short description. Well, if its position changed by 10 meters in 10 seconds, it was moving at a constant velocity. The slope of a P versus T graph is the velocity. From 10 seconds to 20 seconds, it sped up. It's still going constant, but its velocity changed from 1 meter per second to 40 minus 10 is 30 in 20 seconds, 30 over 20, or 1.5 meters per second. So it was traveling at a constant speed, 1 meter per second, sped up to 1.5 meters per second from 10 seconds to 20 seconds. And then its position doesn't change. So it stopped at 20 seconds when it was 40 meters away from us. Okay. So a man began gaining speed with an acceleration. He has no acceleration here. The acceleration is the change of velocity. So instantaneously, his velocity changed here, and instantaneously, he decelerated here, but there's no acceleration change from 0 to 10, or from 10 to 20, or from 20 to 30. So this part is wrong. He didn't begin to gain speed. He was already gaining speed. So a person walked 10 meters of the path during the first 10 seconds. For the next 10 seconds, the person walked at a speed of 3 meters per second. I guess, 3 meters per second. I did that math wrong in my head. This one initially walked at a speed of 1 meter per second, increased its speed to 3 meters per second, and after 20 meters or 20 seconds of walking, stopped. Well, that's kind of right, except we don't know, this isn't telling us anything. We don't know where his speed increased. So the most correct answer so far is number 1. And then initially, a person walked at a speed of 1 meter per second, then walked at a speed of 2 meters per second. This is not true. And then for 30 seconds, he walked at a speed of 1.3 meters per second. Well, no, he didn't. In the first 10 meters, he walked, or first 10 seconds, he walked 10 meters. In the next 10 seconds, he walked 30 meters. I said 30 over 20 earlier. It should have been 30. He went from 10 to 40. So he went 30 meters in 10 seconds. And then he didn't walk at all for the last 10 seconds. So the most accurate story here is B. And it's just being able to read what you're seeing on the graph. And that's all. That's really all chapter 1 was even about, was understanding some graphs, understanding some unit conversions. Chapter 2's homework, however, is a little bit more exciting, let's say. Now we're going to go on to the vector assignment. And this assignment, really, I just want you to be able to break up vectors. We're going to talk, there's a couple problems on here that are like things that we're going to do, but a few of these are just breaking vectors up. Breaking vectors up goes back to SOHCAHTOA. And if you don't know what SOHCAHTOA is, right triangles. So any right triangle has a 90-degree curve. This angle and this angle. We're only going to concentrate on that angle down there though, which is theta for now. And this is our hypotenuse. This is our opposite of the angle, and this is our adjacent. And what SOHCAHTOA tells you is sine of the angle is SO is opposite over hypotenuse. And cosine of our angle is adjacent over our hypotenuse. And tangent of our angle is TOA. So this is ka, and this is TOA, is opposite over adjacent. Now you probably know this a little bit better as the following. If this is a vector, then the vector has components. Let's call this vector R at some angle. Then R of X is the magnitude of R, whatever its magnitude is, times cosine of the angle. And what that comes from is, since cosine of the angle is the adjacent over the hypotenuse, then the adjacent, or X part, is the hypotenuse times the cosine. Similarly, Ry is the magnitude of R, however long it is, times sine of the angle. And any vector can be broken up into its constituent parts, Rx, Ry. We call those components. The reason why we do that is it's easier to break our vectors into components, solve the X motion, solve the Y motion, and then we put them back together. And how you put a vector back together is the magnitude of R from the Pythagorean theorem, hypotenuse squared is equal to X squared plus Y squared. The magnitude of R is its X plus its Y squared. To prove that really fast, this would be R sine, cosine squared, R squared plus R sine squared. Now I can pull the R squared out, and the square root of R is just the R squared. The square root of R squared is just the magnitude of R. And I'm left with cosine squared plus sine squared. But cosine squared plus sine squared is 1. So you can see that that will give you the magnitude of R. Finally, if we use, and we normally will give a vector from the x-axis, our angle, if we multiply arctan by both sides, we get that the arctan of our angle is Ry over Rx. And so those two things we're going to use a bunch, actually all three of these. This definition, this definition, this definition of the magnitude, and this definition of tangent. All right, so our first one is we want to know the x component of the vector e. Now, if I take this vector e and I make a right triangle, so this is e, and this is some angle, and this is my x-axis, and this is my y, then the x component here is e of x. Well, we already know that the x component of a right triangle is this part. So the x is r cosine theta, if this is r. But one thing that you do need to realize is this angle is negative. However, something important, cosine of an angle is equal to cosine of a negative angle. Sine of a negative angle, however, is negative sine of that angle. So we can just write ex as e cosine of the angle. If I look here, what is the x component shown? Now there's one other quick thing here that we need to note, and that is that when we have an angle, okay, this is 90 degrees. So if I call this guy and this guy, one thing I can see is that I have a triangle that looks like this with phi. This part of it, of phi, is e cosine phi. However, I also have a triangle down below that looks like this. And this is my hypotenuse for this one, and this is my hypotenuse for this one. So that this part is actually the y. This is actually e of y, and it is e cosine of theta. This part is actually now my x, and it is e sine of theta. So this part, which is my y, is e sine of theta. So we want this leg right here, and we can write that as e sine of theta. They don't want this angle, they want this angle. The part along x is e sine of theta. It's that vector. Okay, what is the y component in terms of the angle? So that is this one down, and that is e cosine, because this triangle that we're making actually looks like this, okay? And this is my x, and this is my y. So my y is down. This is my EY. And so if I turn this, it looks like this. Don't let it confuse you. EY is going to be E cosine. I know I'm harping on that, but some people need to really like play around with these triangles. And it goes downward. And EX goes to the right. And it is this guy, which is E sine, okay? Now, one other thing that we need to remember though, is that sine has to have a negative angle. Or better yet, this is going to be a negative value because you can see that this is along the negative y direction. It's going to pick up a negative sign because it's along negative y hat. Now, for the same vector, what is x in terms of phi? Well, x in terms of phi is e cosine. Okay, it's the x component of e along there, and we're using phi now. And what is e of y? It is now this vector that goes down, and it is negative e sine because this angle is negative. It's below the x-axis. It's in the negative y direction. Okay, so just make sure you understand those things. You can identify different components of a vector based on right angles. All right. Let's see. Now, one of the other things that we need to talk about is we can be given, say, a vector r. And let's say we have a vector r that points from the origin to 2 and 1 in the y and the x. Now, our vector we can write as as 2 in the x hat plus 1 in the y hat. The magnitude of this r would be 2 squared plus 1 squared. So it's, let me actually do that symbolically first. It's the rx, the part in the x hat, and the part in the y hat. So that would be 2 squared plus 1 squared, or square root of 4 plus 1 is 5. Now this angle here would be arctan of ry over rx, and that would be arctan of 1 over 2, or a half. So what is the arctan of a half? It is 26.6 degrees. But we can also write r as the vector that has a length of 5, whatever it happens to be in units, at 26.6 degrees from the x-axis. That's another way of writing this vector if we want. And when we do that, you would start at the origin, and at an angle of 26.6 degrees, you would draw an arrow that's square root of 5 long. Okay, so what they're giving us here is 2 vectors. Vector C is 3.25 at 15 degrees. Let me actually draw it this way. 3.25 meters at 15 degrees above the negative x. So if I draw this, and this is my x and this is my y, C is actually at 15 degrees here, and it points like that. This angle is 180 minus 15, or 165 degrees. So we could also say this is 165 degrees from the positive x-axis. Now D is 31.6 at 30 degrees to the right of the negative y. Okay, so the y goes down negative, and it's 30 degrees to the right. So that angle is 30 degrees from there. If we go this way, this is a 90 degrees, so this is at negative 60 degrees is this angle, which I'll just call phi, or angle D, or whatever I want to call it. But it's also at, since there's 300 degrees, if we went all the way around, it's 360. But D has a length of 31.6 meters. And we'll use that in a minute. So we have these 2 vectors, and we're going to find the components of them. So how do I find the components of C? I have a vector, C. Take the angle from the positive x. You don't have to, but the angle from the positive x is 180 minus 15, or 165 degrees. C of x is, again, this is a triangle, but C of x is C, the magnitude of C, times cosine of the angle from the x-axis. So cosine of 165. If you put in cosine of 15, you will have to take the negative value. This is our C of x. Okay. Cosine C of x is C cosine of 165, or negative, because it points along the negative x direction, or negative cosine of 15. All right, well, that is 3.25 cosine of 165 in the x hat direction. Cy is C sine of 165. You can actually use C sine of 15, because this angle here and the angle from that will both give you the same number. So you can use sine of 165 or sine of 15. They'll both be positive. So that means Cx is 3.25 times cosine of 165 negative 3.14 in the x hat direction. Cy is 3.25 sine of 15. You can check for yourself that 3.25 sine of 165 gives you the same thing, 0.084 in the y hat direction. So C is a vector that if I go in the negative x-axis, negative 3.14, and I travel upward 0.84, negative 3.14 meters, travel upward 0.184, I will get the vector C. All right. So negative 3.1 is what they use. They only use 2 sig figs. So negative 3.1 and 0.84. That is your X and your Y. You can see that this is how it points. Okay, so you can visualize this. Now for the D. D, on the other hand, X and Y. And D is 30 degrees away from, D is 30 degrees from the negative y-axis. If I go all the way around here, this is 60 degrees, and there are 360 degrees in a circle. So we can actually write D as a vector that is 31.6 meters is the magnitude of D. And it is at 300 degrees from the positive x-axis that way. You could also go and say it's at negative 60 degrees from the positive x-axis if you want. Doesn't matter either way. Always draw these though and get your angles correct. So this triangle for D, the angle of D when it goes all the way around. But this triangle means that D of X is going to be D sine of 30 or D cosine of 300 or D cosine of negative 60. Any of those will work. I'm going to use the full 300 degrees. So D of X is 31.6 cosine of 300. And that value is 31.6 times cosine of 300, 15.8. Now, you could also, and these aren't meters, you could check for yourself that 31.6 cosine of negative 60 gives you the same answer, or that 31.6 times sine of 30 gives you the same answer. They all give you the same answer. This is our X component. This is this component. The Y component, dy, will be the magnitude of D times sine of 300 degrees. We have to be a little bit more careful because that will be the sine of that. This should give us a negative number. If we use D cosine of 30, so we go with just this angle, we need to put a negative sign there because we know it's in the downward direction, but it'll give us a cosine of 30 will give us a positive answer. Or we can actually compute it from this guy, and that will be D sine of, D sine of negative 60. And all of those will give us the same answer. D is 31.6, so 31.6 sine of 300 gives us negative 27.4 in the y-hat direction. I think they're meters, right? But 31.6 times cosine of 30 gives us positive 27.4. But remember, negative sign because we know it's down, but the calculator doesn't. And then finally, 31.6 sine of negative 60 also gives us negative 27.4. So our answer on this one is 15.8 and negative 27.4. They rounded both of them to 2 sig figs, which is a little weird because they gave us 3 sig figs in our answer. But anyway, 16 and negative 27 is the correct answer. All right. So just make sure on this one, you know how to find all your different components, dx and dy. There are many different ways you can do it. They're showing you 2 of them. You can also go 300 degrees from the x-axis and just do cosine and sine. So, all right. This next one is about adding vectors. Remember that when we add vectors, let's just do 2 easy ones, A and B. So let's say I go A in the X direction, and then I go B in the Y direction. And I want to know how far away I am. So I want to know if I go A and then B, how far away do I end up? I draw a vector from the origin to the tip of B. To add A and B, I set A at the origin, I add the tail of B at the tip of A, and then I draw a vector from the origin to the tip of B. If I walk these, when I walk in the positive direction, I get a positive vector. Walking in the positive direction of B, but I walk backward along R, which means R is negative because I'm walking opposite the direction that R points. I end up back at 0. If I move R over, if I add R to both sides, I see that R is equal to A plus B. However, this isn't quite a math equation yet. R of X is equal to AX plus BX, and R of Y is equal to AY plus BY. So I would need to find the components of A and B so I can add them together and find R, and then obviously do what we've been doing before, R squared plus RY squared. And the angle of R to the x-axis is arctan of RY over Rx. Okay, then let's look at what we're trying to do. So I'll move this down just a little bit, just so we can read this. Okay. So Ruth sets out to visit her friend Ward, who lives however far away. Why? No. That didn't go up to the actual question. So, who lives 41 miles north and 100 miles east of her. So on a compass, north, east, west, south, that means north is Y, east is positive X, west is negative X, and south is negative Y. So she's going to start off driving east, and after 40 miles, so her first vector, which I'm going to call A is 40 miles in the X hat direction, in the positive X direction. She comes to a detour that takes her 15 miles south. Okay, so she goes 15 miles to the south, and that'll be B. And B will be negative 15 miles in the Y hat direction. She then drives east for 8 more miles. So C will be 8 miles in the X hat direction, and she runs out of gas. So Ward flies his small plane to get her, okay? What is Ward's displacement vector? So Ward is at a point 40 miles. So if I go to 40 in the X, 100 in the X and 40 to the north. So he's at a point somewhere here, not to scale. Maybe I should draw this a little bit better to scale. Y and X, or north and east. She went A, B, C, and then he is at a vector all the way out here, that has 40 and 100. Okay. Nope, I flipped those. Sorry. 40 and 100. 140. 100 east, 40 west. So that is going to be, I'm going to call that guy Ward, because that's where his position is. He's going to fly from here to here, and we need to figure out what R is. We need to find the vector from where he is to where she is. Now, how we do this is walk. We get A plus B. B is also in the positive direction. C is in the positive direction. R is negative, and W is negative. And we end up back at the origin. So what we see if we add R to both sides, it's our vector R is A plus B plus C, add R, minus W. And that means that our X is AX plus BX plus CX minus WX. And our Y is AY plus BY plus CY minus WY. Okay. AX is 40. BX is 0. B has no X component. CX is 8. And WX was 100. And just doing this simple math, 40 plus 8 is 48, minus 100 is minus 52 miles in the X hat direction. He has to fly backward. He's got to fly this way, 52 miles. And then he's going to have to fly south. So we know that our Y will also be negative. AY is 0. There's no Y component to A. BY is negative 15. CY is 8, or is 0. And WY was 40, but it gets a negative. So he's got to fly 55 miles south, or 55 miles in the negative Y direction. So this is negative 55 miles, okay, in the Y hat direction, or south. He's got to fly 52 miles west and 55 miles south. All right. 52 and 55, they're both negative because west is negative and south is negative. What is the magnitude of his vector? Well, coming back to here, this is negative 52 and negative 55. So 52 squared, the negative sign cancel, plus 55 squared, take the square root of that answer, and I get 75.7 or 76 miles. Okay, 76 miles. They're just shoving that all in there that way. What is the direction? And now arctan, angle of Ward, is arctan of his RY, and his RY was negative 55, and his RX was negative 52, right? That's how far he went. So your calculator, however, will not, if I put negative 55 divided by negative 52, it's going to give me this angle right here, 46.6 degrees. That is the arctan of negative 55 over negative 52. However, if I look at my picture, I know that this is actually in the third quadrant. So it's somewhere between 0, 90, 90, 180, somewhere between 180 and 270. When you put arctan in your calculator, if you're in the opposite quadrant, so we actually want him to be here, we can add 180 degrees. So add 180. And it's just because your calculator gives you between 90 and negative 90 degrees. So plus 180 is 226.6, 226 degrees is our direction. The heck is that even saying? Oh, I'm sorry. It says to measure your answer in degrees measured clockwise from the negative y-axis. All right, let's see if we can parse that out. This is our negative y-axis. Okay, and we're going to measure them. Oh, I'm sorry, that's our negative x-axis. I'm dumb. Sorry, guys. I'm dumb today. This is our negative y-axis, and I wanted to call it my negative x-axis. And we're going to measure clockwise, which means the way a clock would. So they want this angle. All right, well, this angle is 226.6, and this angle is 270. So they want 270 minus 226.6. So 270 minus 226.6 is 43.4 degrees. This angle is 43.4 degrees. Why? I don't know. They're just making it annoying on you. So it's about 43 degrees. So when you find this angle is actually 90 minus this angle. Why? And I'll show you why. So whatever this angle is that he's flying at, this angle, okay, by law of similar triangles and that angle are the same angle. Just like this angle and this angle are the same angle. So whatever angle this is, and we got, what did we find? 46.6 degrees. Because this is a right, this is 43.4 degrees. And therefore this is 43.4 degrees, and this is 46.6 degrees. Now, if you don't believe me on that, try a steeper angle. Okay. If this is, say, 10 degrees, this is 10 degrees, and this is 80 degrees, and this is 80 degrees, something like that. So, yeah, it's just mastering physics being weird and not telling you what they actually want. But you can also follow this video tutorial that will take you through it slightly differently than I will. Hopefully that's available to you. All right. This one, however, is actually kind of fun. Pine cone falls straight down from a pine tree growing on a 28-degree slope. And the pine cone hits the ground with a speed of 15 meters per second. So let's try to visualize this. We have a pine tree. And this is my pine tree. And it has a pine cone that's going to fall straight down. Okay. Now, the slope is 28 degrees. And what we want to know is what is the component of the pine cone's impact velocity parallel to the ground? All right. So first of all, let's look at this in a weird way. Okay. So if we turn this on its side, it looks like the pine tree is growing straight up. Okay. Straight up and down. And we need to figure out what this angle here is, or that angle. So if we do that, let's redraw it, and we see that this falls at a 90-degree angle. So this angle right here is the same, and this angle right here is the same. Okay, because this is also a 90-degree angle. So I have a vector that is the pine tree's velocity, or even its displacement. They're in the same direction. And it's at 28 degrees. Now, they said parallel to the slope. So they want this part, or this part of our velocity, the part along the slope. I don't know what to call that. So I'm going to call that 2 lines. So V double lines is the magnitude of V times the sine of 28 degrees. The reason for that is, again, if you look at this is a right angle, and this is a right angle. So this is a right angle. And if I come up here, this is my angle on my slope. This is the angle along there. And this is also the angle of my slope. And I want that vector. Anyway, now, I don't know why they changed the angle to radians. They didn't need to, but so 15 meters per second times sine of 28 degrees is 15 sine of 28 is 7.04 meters per second or 7.0 meters per second. I don't know why they did this. They changed it to radians. The only time you need to do radians is if the degrees or if the angle is outside of an argument, meaning, all right, so what is the perpendicular? So if we look at this, we now want this part be perpendicular to the ground, the part that's 90 degrees. And that we can see from this triangle should be cosine of 28 or 15 cosine of 28. 15 cosine of 28 is 13.2, so about 13 meters per second. And it's negative because it's down. I forgot there's negative sign because it's down. Okay. Kind of crazy, kind of weird. But again, to go through this nice and slow, we have this angle and we have a tree that is growing and it's going to drop a pine cone straight down. We can move a vector anywhere we want. So I'm going to actually make this go all the way down. I can't draw a straight line to save my life. All the way down. This is its B. You see that this is a right angle. So this is some theta or B. Okay. But what we need is to figure out what is this angle here. Okay. Now, what we know is that if we turn this on its side, this is our angle of our slope. This is our tree. This is, again, B of it falling 90 degrees. So we need to find this angle right here, this angle. And this angle, phi, okay? But what we do know is if we draw the slope again here, this angle is the same phi, and this angle is therefore theta. So what we have is we have a vector v at an angle theta, and the components of v parallel to the ground are sine of the angle and negative cosine of the angle. Perpendicular. So this is v, we call it perpendicular, this is v parallel. And that's it. Just drawing similar triangles. It takes a little getting used to. But try drawing it for yourself and seeing if you can prove to yourself that this angle is the same as this angle, and then therefore this angle will be the same angle as that. And the trick here is that this is a 90-degree angle. So those two angles have to add up to 90 degrees. And this is a 90-degree angle. So those two angles have to add up to 90 degrees. So weird problem. A lot of times it's what we have to do in physics. All right. The next two are more what we do with vectors. Moving around and finding resultants is one thing, but this is what we tend to do. If we have an object that multiple forces act on, we try to figure out what are the net forces, or maybe the missing forces. So this shows 3 ropes tied in a knot. One of your friends pulls with 3 units of force, another pulls with 5 at 100 degrees. So one's pulling along X, one's pulling along Y. And you need to pull it so that it doesn't move in the X or Y. So let's draw this. So we have one vector that I'll call A, which is 3 in the X hat. And I have a vector that I'll call B, which is 5 newtons at 120 degrees. And then you are going to pull at some angle below. and some unknown. So C is going to be U. But what we do know is that in the X direction, okay, R, or the total, I should say this. I know that AX plus BX plus CX all need to end up being 0. And AY, BY, and CY all need to equal 0. Because when all 3 are pulled, it's not going to move. It's kind of hopeless to do this as a 2-dimensional problem, but we can turn it into 2 1-dimensional problems. Find the X and Y components of each of these 3. So A has an X component of 3 in the X axis. A has a Y component of 0. You look. B has an X component of 5 times cosine of 120 degrees in the X axis. B has a Y component of 5 in the sine of 120 degrees in the Y hat. Okay. B is at 120 degrees. It has 5 units. So my point is that I need to find CX and I need to find CY. Well, CX is equal to negative AX minus BX. Move AX and BX over. And CY is negative AY minus BY. All right. So negative 3 minus 5 cosine of 120 in the X hat direction. Now, negative 3 minus, minus 5 cosine of 120 gives me negative 0.5. Okay. This is minus cosine of 120. This is actually on the same side as C, which is why it's positive. This is 0 minus 5 sine of 120. So minus 5 cosine or sine of 120. And I get negative 4.3. So CY is negative 4.33 in the Y hat. And so my C goes to negative 0.5 in the X and negative 4.3. Negative 4.33. So it looks something like this. This is what C looks like. Now, if I want the magnitude of C, it is CX squared plus CY squared, or negative 0.5 squared plus negative 4.33 squared, which is 0.5 times 0.5 plus 4.33 times 4.33. Square root of this answer, 4.4. And the angle is again the arctan of CX or CY over CX, which is the arctan of negative 4.33 over negative 0.5. But again, it's probably going to give me an angle here. So I need to add 180. So arctan of negative 4.33 divided by negative 0.5, it says 83.4 degrees. So this is also 83.4 degrees. If I add 180 to that, I get this angle. So plus 180 is 263 degrees, 263.4 degrees. This gave me 83.4, but I had to add 180 because my calculator doesn't know that it's supposed to be in the third quadrant. Okay, so how hard must you pull? How hard is the magnitude of the vector? 4.4. 4.4 is the magnitude of C, this vector downward. Okay. In what direction must you pull? Well, you could go, since this is 83.4 degrees. This is 83.4 degrees. This is another one of those where in what direction much you pull on the third rope to keep the knot from moving, they want this angle. See in the picture, they want this angle. This angle is 83.4. I think they're doing that to help you so you don't have to add 180. But honestly, this angle that they're asking is 83. Again, yours might be different. All right. Again, for forces, the net force on the object is F1, F2, F3, F4, and they gave you the net force, once you're done with all of these, is in the I direction. I is just another way of writing X, J is another way of writing Y. And what they're saying is that when you add all four of these up, okay, you get F in the J and F in the I. Let's actually flip those. F in the I and F in the J. And that's going to be AI plus BI plus CI plus DI and AJ plus BJ plus CJ plus DJ. Now when we look, or man, I guess I should call these 1, 2, 3. So let 1 be A, etc. Now, 1 is 5 newtons in the negative J. So -5 in the J hat. This is 0 in the I hat. Plus. 3 is unknown and 4 is unknown. But F2 or F2 or FB as I'm calling it is 6 newtons at 20 degrees. 6 newtons at 20 degrees. So FBI and FBJ are equal to 6 newtons at cosine of 20, 6 newtons at sine of 20. So 6 cosine of 20 is 5.638 in the I hat direction, and 6 sine of 20 is 2.052 in the J hat. So I don't know what BI is. And oh, I'm sorry. So F2 or FB as I'm calling it is 5.638. And I'm going to get rid of these I's really fast. They're just going to cloud me up. And BJ is 2.052 plus. Now, C is F3, and that is unknown, but it's only in the J hat direction. So there's no CJ. There is some, I'm sorry, there's no CI. There is, however, a CJ hat. And D is only in the negative I direction. So there is a DI and there is no DJ. Okay, so we're going to get the following to try and do this on a new page. And I'm going to do it this way. F net in the I hat and F net in the J hat. Leave a blank space for a second. Now, this is, if I look at this, 5.638 plus F4 in the I. Okay, and this one is -5 plus 2. So -5 plus 2.052, -5 plus 2.052 plus F3 in the J hat. Now, when I look at this, so in the X, I have F2's X component and F4. In the Y, I have F3 plus F2's y component minus F1. Minus F1, F2, and F3's. But it tells me that the net has no j component. It does, however, have an I component of 4. Okay. So getting rid of, ignoring the I components for a second, what I have is I have 4 is equal to 5.638 plus F4 in the I hat direction. Subtract negative 5.638, and I get that F4 in the I hat is 4 minus 5.638, or negative 1.638, or F4 has an I component of negative 1.64. It has no j component. Similarly, if I want F3 in the j hat, or F3's j hat component, moving both of these over since they're equal to 0 is 5 minus 2.052, which is 5 minus 2.052, which is 2.948. So 2.95 in the j hat direction. And so I know that F3 is 2.95, F4 is 1.64, but it's in the negative direction. Okay. So what is F3? They actually rounded it to 2.9. I don't know why they rounded it to 2.9. I think they rounded soon, but F3 has a x component of 0. You can see this. And it has a y component of 2.9 or 2.95 is what I got. They got 2.94. I don't know why. Maybe I did something stupid. Now, what are the components of F4? Well, F4 has no y component, and it has a negative 1.6 component in the, so it's only in the x direction, the I direction. Okay. But the idea here is that you're told that F1 plus F2 plus F3 plus F4 are equal to Fnet. You're also told that Fnet has a component in the I or X of 4 and in the J of 0. That's what this means. It's 4I plus 0J. So you can find all the components in the X or I, add them all up to find the missing component in the X, which is F4. Then you can add up all the Y components. Add up all the X components. So the X component of F2 and the X component of F4, and set them equal to 4. And then find F4. You can add up all the components in the Y. So F3, F2's Y component, F1, and set those equal to 0. Because it has no component in. Yeah, it's just adding things up. All right, finally, this last one is kind of important. So doesn't seem very important, but it actually is. Cami is walking through an airport and she's pulling her suitcase at a 42-degree angle from the vertical, parallel to the handle with a force of 110. So her suitcase looks something like this. And she is pulling on it with a vector of 120 newtons. They gave us, so let me just put it here, they gave us this angle as 42 degrees, okay? 42 degrees from the vertical angle. Now, what is the magnitude of her horizontal part of her force? So we have a vector at 120 newtons that makes an angle of 42 degrees. You can do one of two things. You could assume that this is our triangle, 42 degrees, our hypotenuse is 120, or since these two angles have to add up to 90, this is 48 degrees, and you could assume this is your triangle, but flip the angle 48 degrees, and again, our hypotenuse is 120 newtons. So our horizontal part is the x part, and that is 120 cosine of 48. The vertical part is 120 sine of 48. Now, if you don't want to change the angle, then the part that's horizontal is actually h sine of 42. So it's 120 sine of 42. And that's because it's this part of this vector with this 42 degrees. And the horizontal or the vertical part of your force is 120 cosine of 42. Cosine of the angle is sine of 90 minus the angle, and vice versa. So you just, if you flip them, you need to flip or subtract or add 90 degrees, depending. Let's use this one. So 120 cosine of 48 is 80.3. And 120 sine of 48 is 89.2. So the horizontal component of her force is 80.3. They're using this one. So they're using 120 sine of 42 or 120 cosine. Sorry, 120 sine of 42, which is the same 80.3 that I used 120 cosine. And then the vertical component, I use sine, they're using cosine. With the opposite angle, I got 89.2, they got 89 or 89.2. Okay, so it's just understanding how to find the components of vectors, understanding triangles. These vector things are hard if you've never done vectors. The best thing I can tell you is learn your SOHCAHTOA stuff. Go back to just right angle trigonometry, wherever that was, where the cosine of the angle is, or the sine of the angle is opposite over hypotenuse, cosine, and just make sure you know how to do this page right here. Find the magnitude of a vector from its components, find the components of a vector from its magnitude and direction, find the angle that it makes, and then play around. Try orienting the triangle in different ways, so that a lot of us are kind of rigid, and it's hard for us to imagine this triangle and this triangle are exactly the same triangles, and this length and this length are just reflections of each other, and this length and this length are reflections of each other. So just try to play around a little bit with your angles and stuff and add your components. Like I said, the most important one is really this one, finding the vertical and horizontal components of the force. On that, that's something we will do. This one, finding all your components in the x, all your components in the y, setting the x equal to 4, setting the y equal to 0, and for the missing forces. And this one, that you know that the forces equal 0 in the x and y because it's in equilibrium, is what we call it. Please go to this one and determining the angle of a vector and resolving the vector components. Review those if you're bad at this. Please, please, please do that. We will do a lot of this type of stuff. This is also very important. Finding the pine cone from an incline, as you'll see in the comments. I would say this type of adding up vectors, we're probably not going to do very much of it all. And this is breaking components, so that one's important. And this is a very simple breaking up of components, but recognizing how to use different angles instead of just the angle that you want. So I would say this is a very important homework assignment for building up your skills with vectors. Probably half of you already are okay on this. Those of you that aren't, really, 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 really make sure you learn this stuff. It will help you in the long run. This is where people cannot, if you cannot find your vectors in the X and Y, you can't solve problems. Anyway, Chris and Eduardo, thank you for being here. For the rest of you that are watching this on recording, I hope it helps. Every week that we have homework, I will try to do this and go through all the problems. And thanks for being here the whole time, guys. Eduardo or Chris, are you guys okay?